So welcome back to this webinar on heat and mass transfer. Today we are solving some problems in radiation. So we have two large parallel plates with emissivity 0.5. They are maintained at different temperatures and they are exchanging heat only by radiation. So we have two equally large radiation shields kept between them. Their surface emissivities are 0.05. So you have been asked to find out the percentage of reduction in net radiative heat transfer because of introducing these two large radiation shields in between these two large parallel plates. So the schematic of this problem can be drawn like this. So we have a plate here 1 and plate here 2. So both these plates 1 and 2 are large and parallel, which means they have no boundaries, and in between these plates we are introducing two radiation shields which are also kept parallel between them. So the emissivities of plate 1 is epsilon 1 and plate 2 is epsilon 2. So for these radiation shields we denote it by epsilon S1 and epsilon S2. So for both these shields, so these are radiation shields. So two plates, their temperatures are T1 and T2 respectively. So now from the data given, we know that epsilon 1 is equal to epsilon 2 is equal to 0.5. Emissivity of both the plates are 0.5 and emissivity of both the radiation shields are 0.05. So the number of shields here is 2. Now we have been asked to find out the percentage reduction in Q due to these shields. So now the heat exchange between these two plates is given as Q12 is equal to epsilon bar, which is average emissivity, T1 power 4 minus T2 power 4. So this epsilon is equal to 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So this is available in your HMT data book. So now we can find out epsilon bar, which is 1 by 0.5 plus 1 by 0.5 minus 1. So epsilon bar will be 0.333. So now let's start solving for Q12. 0.333. Sigma is your Stefan Boltzmann constant, A area, and T1 power 4 minus T2 power 4. So this is your equation for radiative heat transfer without shield. So now we are going to calculate the radiative heat transfer with shield. So let's solve that one. So with shield, so for this we have an equation which is already. For heat transfer with shield, we have an equation from the data book which is A sigma T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 plus 2n by epsilon s minus n plus 1. So this will be your equation which is available in the data book. N is the number of shields present. Sigma s, epsilon s is the emissivity of the radiation shields. So now we can directly find out the heat transfer with shields between 1 and 2 using this equation. Now let me substitute the knowns here. So A sigma T1 power 4 minus T2 power 4 divided by 1 by 0.5 plus 1 by 0.5 plus 2 into 2 shields. Each of them have this emissivity of 0.05 minus 2 shields plus 1. So this will be A epsilon T1 power 4 minus T2 power 4 divided by this one. If you simplify, this one will be equal to 81. So your Q with shield is equal to 0.0123 A sigma T1 power 4 minus T2 power 4. So now we have another equation for with shield. So this is an equation for without shield. So now let's find out the percentage reduction in heat transfer due to this shields. So this will be like Q without shield minus Q with shield divided by Q without shield. So Q without shield we already found out, which is 0.333 sigma A T1 power 4 minus T2 power 4 minus T1 power 4 minus T2 power 4 minus 0.0123 A sigma T1 power 4 minus T2 power 4 divided by 0.33 sigma A T1 power 4 minus T2 power 4. So you can cancel out the common terms here. So finally you will have an equation simplified to this, which is equal to 0.963 or 96.3%. So this will be your percentage in reduction.